Welcome to another CSI training program. Here at CSI, we are seriously committed to the success of your reliability-based maintenance programs, using predictive and other proactive maintenance methods. Applying the tips and techniques in this program, gear analysis will enhance your RBM program, increasing uptime on gear-driven equipment due to the ability to accurately determine gear drive condition. A single-channel vibration analyzer such as this one can be used to determine the gear condition and pinpoint the problems, as well as determine the severity of the problems. We will use spectral and waveform data to show how to distinguish these faults and outline the best setups and measurement point locations for acquiring the best data for accurate diagnosis. Some of the common gear problems detectable with vibration analysis include gear wear, chipped or broken teeth, gear eccentricity, component misalignment, gear misalignment, improper backlash, looseness, gear resonance, hunting tooth problems, and improper meshing due to manufacturing errors. This program focuses on the most common problems: gear wear, chipped or broken teeth, misaligned gears, backlash, and transmission error, as well as the effects of load. Each of these gears has particular characteristics due to its design and use that affect the data, and therefore the analysis steps. Some gears tend to show problems in specific measurement points and camouflage problems in another. Recommendations will be made for the various gear types. Although these two gears look very different, they still perform the same job: transmit torque and change the speed without slip. The ability to run at high speeds, the relatively low cost of the torque transmitted, and the high power to size ratio make gears the drive of choice in most industrial applications. The power can be transmitted in line, such as this gearbox, or at an angle. In either case, the speed of the driven unit can be increased or decreased, and thereby affect the transmitted torque. Gearboxes are generally thought of as very complex machinery components, and therefore too difficult to analyze. However, if we understand some of the basic theory and design of the gearboxes, then we will be able to more accurately determine the problems associated with them. Since torque and speed are transmitted through the teeth must be designed to reduce wear and vibration, thereby increasing tooth life. As these teeth mesh, the clearances must be maintained, and the contact surfaces must achieve a constant force to create the longest life and smoothest operation. For smooth gear operation, two criteria for the teeth must be met. When two teeth meet, they have a common tangent. A tangent is simply a straight line that touches the circle or curve at one point. The teeth each have the same tangent at the mesh point of the teeth. They are then said to have a common tangent. When a line is drawn perpendicular to the tangent at the point of the tooth mesh, it is called a normal to the common tangent. This normal to common tangent intersects a line through the center of the gears. This point of intersection is called the pitch point. The next teeth that mesh will also define a pitch point. A circle connecting the pitch points is called the pitch circle. The diameter of this circle is called the pitch diameter and is used often in defining gear size. The speed of a gear is defined as the speed along the circle and is called pitch line velocity. ANSI-AGMA, American Gear Manufacturers Association standards, are set using the pitch line velocity to categorize them. When gear teeth are designed and manufactured with this first criteria, that is, the normal to common tangent passing through the pitch point, then the gear will operate quieter and with less vibration. The second criteria is met when this pitch point is on the center line of the gears. These criteria help ensure a constant speed or constant velocity of the gears and maximizes gear life. The term for these two criteria is conjugacy. A gear set that does not meet these conditions for conjugacy constantly adjusts the speed to compensate for imperfections and severely reduces gear life. As the gear rotates to mesh with another tooth, the tip of this tooth is still on the normal to the common tangent line. As this tooth begins contacting, some of the force is reduced from the first tooth and shared by this new tooth. This changing of the pressure causes changes in the deflection of the teeth. Gear teeth can have many shapes and meet the condition of conjugacy, but most are unsatisfactory for modern gearing. The most common tooth shape is the involute. The involute is the curve traced by the end of a tight string, as it is unwound from the circumference of a circle. There are many benefits to this tooth shape. Small errors in the center-to-center distance of the gears do not violate the meshing action. Another is the common tangent and the force always act in the same place and the same direction, producing the lowest noise and vibration levels. Gear shapes may differ vastly, but can have the same tooth shape. This helical gear is different from the spur gear, but the tooth shapes are the same. The angle of the teeth can vary substantially depending upon the intended use. A helical gear typically has 1.5 teeth contacting through each revolution, while the spur gear has one set contacting half of the time and 2 sets of teeth contacting the rest of the time. This means the maximum stress a spur gear drive can carry is limited to the stress capability of only one tooth. The helical gear can typically carry the stress equal to 1.5 times the stress limit of one tooth. In addition, since the teeth mesh by starting at one end and moving to the other, there is an averaging effect on the tooth profile errors, so that the drive runs much smoother than the spur gear arrangement. The primary disadvantage is the slanting or spiral tooth design creates strong axial vibrations, which is rarely seen in spur gears. Some applications use a double helical configuration, which is essentially 2 helical gears back to back. These can be placed on the shaft in such a precise location that the axial forces cancel themselves out. When 2 sets of helical teeth are cut on the same gear and intersect each other, they are called a herringbone pattern. Bevel gears are similar to helical gears, except that they are cut on a cone shape and work with intersecting axes. The teeth can be either straight cut or spiral cut like these. A common application is a right-angle drive. They are similar to spur gears in their operation, but are much more sensitive to assembly dimensions. They should not be used for high-speed drives or where extremely high accuracy is required. Another gear type is the worm drive. The worm drive uses a shaft called a worm gear and meshes with a gear called a worm wheel. The worm gear has teeth like threads of a screw. Usually, more than one thread meshes with the worm wheel. These are typically used where a high ratio is required in right-angle drives. All these gears must be machined to a very close tolerance because any errors will be magnified in the meshing action and decrease gear life. For proper meshing, the gears are placed so that the teeth of one gear do not bottom out in the other gear, and only one side of the tooth should make contact. The back side of the tooth, including the tip, should not make contact during the meshing action. This clearance on the back of the teeth is called backlash. When the gears are heavily loaded, the teeth will bend or deflect, decreasing the tolerances. The tolerance must be such that the meshing action will not allow contact on the back side of the teeth. All of these design considerations affect how well the gears perform transmitting torque and reducing or increasing speed. A good design will have low noise, smooth operation, better transmission, and longer life. A poor design will have loud noise and excessive vibration, and transmission error will reduce the life. Another important design factor is the ratio of the teeth on the meshing gears. A gear should have a number of teeth that would cause a single tooth on the first gear to contact every tooth on the mating gear. When this is true, the gear set is said to have a proper ratio. Any imperfections in a tooth will transfer to all teeth rather than imprinting just a few teeth with the defect. For example, if a gear has 12 teeth and meshes with one that has 36 teeth, then a tooth on the first gear will only contact 3 teeth on the mating gear. Any tooth problems will then be transferred to the 3 teeth and cause accelerated wear of those teeth, increasing the vibration of the gear train and decreasing life. Comparing the number of teeth on each gear and factoring them to their prime numbers will determine whether the ratio is a proper ratio. A proper ratio will have no other common factors than 1. A prime number is a number that cannot be divided by any number other than itself and 1. Prime numbers are 1, 3, 5, 7, 11, 13, 17, and so on. The number 12 can be reduced to 1 times 2 times 2 times 3. The number 15 can be reduced to 1 times 3 times 5. 12 and 15 then have only one factor in common, 3. This common factor plays a significant role in determining some gear problems, as we will see later. Another example is a 52-tooth gear meshing with a 16-tooth gear. 52 can be factored to 1 times 2 times 2 times 13. 16 can be factored to 1 times 2 times 2 times 2 times 2. The factors these numbers have in common are 2 times 2. So the common factor is 4. A good gear set will have a proper ratio. That is, the common factor will be 1. An example is an 11-tooth gear meshing with a 17-tooth gear. The only common prime factor is 1. A gear set that has any other common factor than 1 is said to have an improper ratio. The ratio is useful in determining the number of teeth contacted by a tooth on the mating gear and other occurrences in a spectrum. The meshing action of the teeth will always generate noise and vibration at some amplitude. Imperfections in the teeth or gears will cause variance in the amplitude. This meshing action is called gear mesh. The frequency of this gear mesh can be easily calculated for any gear set. It is simply the number of teeth on a gear times its shaft speed. For example, for an input shaft speed of 1200 cycles per minute with 24 teeth on it, the gear mesh frequency is 28,800 cycles per minute. Since the frequencies tend to be high, we commonly express the frequencies in cycles per second or hertz in order to work with smaller numbers. This would make the input speed 20 hertz and the gear mesh frequency 480 hertz. The mating gear is 150 teeth, and its shaft speed is the ratio of the 2 gears. Simply divide the teeth of the first shaft by the teeth of the second shaft to obtain the ratio. This yields 0.16. Now multiply the input shaft speed by 0.16 to obtain this shaft speed. So 20 hertz times 0.16 equals 3.2 hertz. This is the shaft speed. Remember that gear mesh frequency is simply shaft speed times the number of teeth on the gear. So 150 teeth times 3.2 hertz yields 480 hertz. Notice that this is the same gear mesh frequency as calculated for the first shaft. It is important to note that the gear mesh frequency will be the same throughout the gear train, where each shaft only has 1 gear on it. This means that the gear mesh frequency will remain constant in a multi-shaft application, where there is only a single gear step from one shaft to the next. Even in a roll process such as a paper machine that has many gears, the gear mesh frequency can be the same through all the rolls of various diameters and various speeds. The only instance where there is more than 1 gear mesh frequency is in a double or multiple reduction gear drive. That is, the shaft has more than 1 gear, and these gears have a different number of teeth. This gearbox has 20 teeth on the input shaft and meshes with a 41-tooth gear on the intermediate shaft. These two will have the same gear mesh frequency. But notice that this intermediate shaft has another gear. It has 14 teeth on it. Now the gear mesh will change for this gear and its mating gear. If this intermediate shaft is turning at a speed of 10 hertz, the gear mesh frequency for the 41-tooth gear will be 410 hertz, while the 14-tooth gear would generate a gear mesh frequency of 140 hertz. Multiple reduction gearboxes, such as this one, can be more difficult to diagnose problems due to the additional frequencies generated. In another program on bearing analysis, we pointed out that bearing frequencies are defect frequencies and should not be present in a good bearing. Unlike bearing frequencies, gear mesh frequencies will show up at some amplitude, even if the gear train is in good condition. The gear mesh frequency may be so low it does not stand out, but it is there. The design of the gears, including the tooth shape, number and spacing of teeth, as well as the machining tolerances, all affect the life, the noise, and the vibration of the gears. The next section takes a close look at some gear faults and how they show up in spectral and waveform data. In the previous section, we pointed out how gear mesh is generated and how it is directly related to the number of teeth on the gear and the speed of the shaft. Here, we will consider the effects of load on a gear set and examine some specific faults and how they show up in spectral and waveform data. The faults we will consider here are gear wear, gear misalignment, chipped or broken tooth, improper backlash, and transmission error. We have pointed out that the various types of gears will tend to show up best in certain directions. The spur gear has very little axial motion, so the radial measurement points tend to be best for analyzing them. Helical and bevel gears tend to show the most information in the axial direction due to their axial thrust. For analyzing gear drives, sometimes the quickest method to determine where to start is by comparing points. Compare the measurement points from one bearing location and select the ones with the highest amplitudes or most information. Next, compare points of the same direction from several bearing locations. This approach can help you zero in on the problem area and save time. Another helpful tool is a simple diagram of the gearbox showing each shaft, the measurement point locations, and the gear locations. It is very important to know the exact input shaft speed and the number of teeth on each gear. These will help in determining exact gear mesh frequencies and other indicators. We expect to see the gear mesh frequency for the gears, and when the gear or meshing action is not correct, the amplitude of the gear mesh may be affected. This gear mesh frequency in the upper end of the spectrum stands out considerably from the surrounding energy. Its amplitude may seem high, yet we cannot use amplitude alone to determine that a gear problem exists. The high amplitude may be due to process variables, not gear problems. One characteristic of gear mesh frequencies indicating a problem is that the gear mesh frequency is modulated by another frequency. This modulation shows up as sidebands around the gear mesh frequency. Sidebands are peaks that are evenly spaced to either side of a frequency. There may be more than one sideband on each side. One side may have more sidebands than the other. For gear mesh frequencies, the sidebands are normally spaced at the frequency of the gear with a problem. Simply set a mark at the gear mesh frequency and move the cursor to a sideband. The distance or frequency between them is the speed of the offending gear. Sometimes there are sidebands of both gears. In this case, the worst gear tends to have the highest amplitude. It is important to note that these sidebands may not be discernible if the resolution is not high enough, especially in the case of multiple frequency sidebands. A second, third, or multiple harmonic of the sideband for one gear may be near the one-time sideband of the other gear, and poor resolution will cause them to appear as one peak. The presence of the sidebands points out that there is a problem, but how severe is it? A good indicator is the number and amplitude of the sidebands. In this spectrum from a pinion stand in a roll process, the gear mesh frequency is at 21 times turning speed. Notice the sidebands spaced around it. They are higher in amplitude than the gear mesh frequency itself. This indicates a more severe problem. In determining severity, the actual amplitude is not as important as the relative amplitude. That is, the amplitude of the sidebands relative to the gear mesh frequency. Typically, the problem is considered severe when the sidebands approach half the amplitude of the gear mesh frequency. In routine PDM programs, it is common to detect problems with gear drives using the amplitude of the gear mesh frequency alone. In this case, the key is the change in amplitude. Although there may not be a serious problem with the gears, other problems such as bearing wear, misalignment, and bad coupling can affect gear mesh and lead to gear degradation. Of course, some problems are obviously more severe than others. A broken tooth can indicate excessive loads on the gear and puts undue stress on the other teeth. Wear adversely affects the gear meshing action, but the gear may run longer than a gear with a broken tooth. How can we distinguish one defect from another? Although gears are generally considered to be high-frequency energy, 4 areas of the spectrum provide key indications of the types of fault. They are the high-frequency area, of course, the area at the opposite end of the spectrum, which is the subsynchronous area, the area including shaft turning speed and its multiples, and the area that falls mid-range between here and the high frequencies. Some of these frequencies can be determined through specific testing, but most of these frequencies can be located by simple calculations if we know the number of teeth on each gear and the precise input speed. A good set of gears with proper tolerances and conform to the standards set by AGMA, American Gear Manufacturers Association, should last 20 years or more. However, bearing wear, excessive loading, and imperfections in the machining and material of the parts can cause the in-service life to be reduced substantially. This spectrum is from the drive side of a paper machine. The peak at 304 Hz is the gear mesh frequency, and the side bands are spaced at 1 times turning speed of the shaft. The energy in the area of 100 Hz is the resonant frequency of the gear. This is a typical example of gear wear. When gears wear, the surfaces tend to strike as they mesh, exciting the natural frequency of the gear. The natural or resonant frequencies can be determined using an impact test. Of course, the testing should be done while there is a load against the teeth, so it will resemble the gear load as it is meshing. The key here is that this resonant frequency will be modulated by side bands spaced at shaft speed. Earlier, we pointed out that the life of gears depends to a large part on the gear ratio. A proper ratio is one in which a tooth on one gear contacts every tooth on the mating gear before repeating the cycle. This is a sketch of the layout of a gearbox that drives a winder. Notice the input shaft has 24 teeth. The mating gear has 72 teeth. With this configuration, a tooth on the input shaft will only contact 3 teeth on the mating gear. This is a good example of what is called an improper ratio. An improper ratio such as this dramatically increases gear wear and reduces gear life. To make matters even worse, there are 2 output shafts, and the speed of them has been increased by using 24-tooth gears. This situation can cause the analyst much frustration as he tries to pinpoint a problem. Gear wear shows up as side banding around the gear mesh frequency and excites the natural or resonant frequencies of the gear. This natural frequency usually has side bands spaced at shaft speed. Sometimes the gears could be so worn that they appear as looseness at the spectral data. The waveform may have a high level of impacting and can exceed 20 to 30 Gs. Gear misalignment causes accelerated wear and an uneven pattern with excessive pitting. When left uncorrected, the gear causes other components such as bearings to fail prematurely due to the additional stress. This case history is from a double reduction gearbox driving a mixer. The misalignment is between the first and second gear. This spectrum from the input shaft is similar to the data shown for the excessive gear wear. The gear mesh frequency is at 15 times turning speed. Notice how the second harmonic of gear mesh frequency has much more energy around it. When the area around 2 times gear mesh is expanded, we can see the detail better. Locating the peak at 30 orders or 2 times gear mesh, we see that it is smaller than the peaks around it. Marking this peak, we move over to another peak to determine the spacing. We see that they are side bands equal to the speed of the input shaft. The 1 times shaft turning speed peak is quite high in the spectrum. It could indicate unbalance, a bent or eccentric shaft, or, like